Hey guys, so today we're going to have a swing at looking at a few more examples for exercise 2G, applications of simultaneous equations. So the first example from the textbook, it looks at two possible methods for paying gas bills. One method A, has a fixed charge of $25 per quarter plus 50 cents per unit of gas used, whereas method B has a higher fixed charge of $50 per quarter plus 25 cents per unit of gas used. You want to determine the number of units which must be used before method B becomes cheaper than method A. Okay, so just looking at creating cost functions for both of those, method A starts out with a cost equal to $25 plus 0.5 or 50 cents per each unit of gas used. Whereas method B, cost, as it's set out here, has a higher starting cost of $50, but then plus 0.25 or 25 cents per each unit of gas used. So you can see that method B starts out as more expensive, but has a lower cost per unit of gas used. So eventually method B will become cheaper than method A, and that's where we want to find. So if we draw that on a graph, you can see that method B starts out at 50, method A starts out at 25, but method B is going at a lower gradient of 0.25 when compared with method A, which has double the gradient. So at a certain point where they intersect there, that's where method B is going to become cheaper than method A. So we can find that is where method A is equal to method B, or where 25 plus 0.5 G is equal to 50 plus 0.25 G. Sorry, just to finish off this graph here, that's the cost on the y-axis, so that's the independent variable, while on the x-axis we have G, or the amount of gas used. So to solve that, we just make G the subject. So we take 25 away, so we got 0.5 G is equal to 25 plus 0.25 G. Then we get G's all on one side, so take away 0.25 G. So we got 0.25 G left. So equal to 25. 25 divided by 0.25 is equal to 100. So that intersection, we know, is at 100 units of gas used. So at 100 units of gas used, from anywhere onwards from there, anywhere higher than that, method A becomes cheaper than method B. Method B becomes cheaper than method A, as you can see there, because the gradient is lower. So anywhere before that, so in this section here, up to 100 litres of gas used, method A is the cheaper one. But after that point, method B becomes a cheaper one. So looking at another different type of example, we won't graph this one. A boat can be hired out for $165 plus 2 litres for every litre of petrol used, or just for a flat rate of $200 per day. Find the expression for each cost function and identify the point at which it becomes more economical to use a flat rate. So the flat rate, pretty simple, the cost is $200 per day. There's no variable, no matter what happens, it's always going to be $200. The other one is the cost would be equal to 165 plus 2p. So for every litre used, where P stands for litres used. So obviously initially, this cost of $165 per day, if no petrol was used, is cheaper than the flat rate. So we want to find when this stops to be the case. So when do these two lines intersect? So that's when 165 plus 2p, don't know what happened there, 2p is equal to 200. So simply you'd get p by itself. So take away 165, I don't know why I did that. So 2p is equal to 35, p is equal to 17.5. So to write that, if you were writing that out, you'd say if the boat owner uses 17.5 litres or more, it'd be more efficient to just use the flat rate. Anything lower than using 17.5 litres, they would need to hire it out just at the